Hello everyone, so thank you to be there today. This is our second session of student links, working at links student pitch. We have 6 students today that will present their work in 5 minutes. And we start with Michel. So Michel, you can start.
Hello, everyone. So during my PhD under the supervision of Professor François Bachelli, we worked on models from computational neuroscience using tools from probability and stochastic geometry. So our base model is to consider a population of neurons as a network where each node represents a neuron, and these neurons interact at random times. The behavior of this network is governed by a set of stochastic differential equations. And so this model is called the Galvez-Loeschebach or GL model. It is a pretty standard model in computational neuroscience. So our goal is to introduce computationally tractable models that mirror the GL model in certain ways and rigorously prove certain limit theorems in these models that we introduce. And another goal that I will only mention briefly in this presentation is to study certain particular geometries of networks following the GL model. Yes.
Michel.
Oui. Oui.
Apparently you are still on the first slide.
Ah. I'm on the second.
Okay.
Let me.
The echo was coming from me. I think now it's okay.
It's okay.
Yeah. No, it's, no, you don't see your slide.
Yeah. Now that's normal.
Yeah.
Okay. Now second slide. For everyone is fine.
Okay. Good.
Okay. So yes, as I was mentioning, secondary objective is to study certain specific geometries for geonetworks, namely cycles, which have been shown to be very important from a biological point of view and which are still poorly understood. But here I'll focus mostly on the first point. So the base GL model consists of, as I said, a certain number of neurons, and each neuron at random times spikes. When it spikes, its value is reset, its state is reset to some base value, for instance, 0, and it increments the state of each of its neighbors by a certain amount, which depends on the geometry of the network. And of course, the higher the state, the greater is the chance for a given neuron to spike and to be reset. And due to the complexity of interactions in this model is not tractable. So a classical approach is to simplify the model by taking the thermodynamic mean field limit. That means letting the number of particles go to infinity and scaling accordingly the weights of interactions as 1 over the number of particles to prevent the explosion of the system, or basically epilepsy. So in this mean field limit, the geometry of the network is not preserved. All the neurons will follow the same state equation that is obtained by considering them to be independent and like the limit of being weakly interacting. So to circumvent this problem, because the geometry of the network has been shown to be biologically relevant in many cases, one way is to use what is called the replica mean field model. In the replica mean field approach, you take replicas of the initial network and you change the interactions. Now interactions become randomly routed between replicas. So if in a given replica, a neuron would spike and interact with its neighbors, instead, for each of its neighbors, it chooses a replica at random uniformly and interacts with the corresponding neighbor in the chosen replica. And our goal is to study what happens when the number of replicas goes to infinity. What we want to do is to prove the so-called Poisson hypothesis, show that in this limit, the replicas become asymptotically independent, and the arrivals to a given node in a given replica become a Poisson process, become a sum of weighted Poisson processes. And this will allow for tractability. And so the advantage of this approach is that the memory of the geometry is retained at the limit through the weights of the Poisson processes and the intensities of the corresponding Poisson processes. And so what we have obtained as results is the proof of this Poisson hypothesis, both in for a large class of models, which we call the fragmentation interaction aggregation processes, or FIAPs for short, in discrete time, and in continuous time in the case of Galvez-Lechabard dynamics, for the Galvez-Lechabard model on compacts of time. And so for future work, we want to generalize, we're working on generalizing current and future work. We're working on generalizing the replica mean field to other kinds of dynamics, not just from neuroscience, and also, as I mentioned, to study cycles of neurons in the GL model, so for specific geometries. In particular, fixed points for the distribution, existence and uniqueness of fixed distributions of fixed points. Okay, thank you for listening. And if you have any questions, I'll be happy to answer them.
Thank you, Michel. Any question in the room? Or on the bridge? I have one question on my side. Yeah, so in this model, I understand that you have some replica, but yes, I have two questions, in fact, that are related. What does it mean first, going from one replica to the other? Is it can it be considered as time evolution or something like this? And what do you mean by going from finite number to infinite number of replica?
So what I mean by that is that interactions happen at random times. So what we do in the replicas approach is that we change the interaction scheme, so to speak. So if a neuron would spike and normally interact with its neighbors, instead for each of its neighbors, it considers one replica at random and interacts with that neighbor in that given replica and not its own. So it kind of mixes interactions in between the replicas. So you can sort of see it on the B slide here. So if the green neuron spikes, for each of its neighbors, it chooses a replica, and basically the state of its neighbor, of this blue neighbor, is incremented by a certain given amount, a mu here, in this replica only. And for the red one, only in this replica, and not across all replicas or not inside its own replica. So it basically mixes interactions to make them replicas more and more independent, and to sort of make the Poisson character appear. And as to what happens, what do I mean when I'm going to infinity? What I'm looking at is that I'm looking what happens mathematically when the number of replicas goes to infinity, and then I'm looking at any characteristic replica, because they all, since they become kind of independent, they all have the same behavior at the limit. So what we do is we look at one of the replicas and we study the dynamics inside any of the infinite number of replicas, so to speak. And the idea is that in this infinite replica model, you don't get a connected graph like in A anymore. You have independent nodes, so to speak, but the intensity of the arrivals that they receive depends on the geometry of the initial network. Okay. Does that answer your question?
Yes, I think I would have to read a bit more about your work to understand a bit better, but it's okay. It's okay for me. Thank you. Other questions? No questions? Okay, thanks. So,
okay, I'll stop sharing.
Next speaker, so Sayeh.
No, okay.
Sayeh, so when you will have 1 minute left, I will say do that, in fact, just to adapt you. Okay. With the people in the room, it's easier, in fact, to do it visually than by chat. Okay, so you can start when you want.
Okay. Hello, everyone. I want to talk about the perfect sampling of a null-recurrent Markov chain, which is my thesis post. In the problem of perfect sampling, we have a Markov chain with countable state space S and transition matrix P, which this transition matrix, when is irreducible, aperiodic, and positive recurrent, it has a stationary distribution pi. That we can talk about the perfect sampling of this stationary distribution. In the case that we don't have positive recurrent Markov chain and we have non-recurrent Markov chain, this stationary distribution doesn't exist. And instead, we have a stationary measure sigma, which it is not distribution in the sense that it is not finite. In the case that the Markov chain is positive recurrent, we can talk about perfect sampling, as I said. One of the algorithms that gives the perfect sample in this case is the coupling from the past algorithm. In the coupling from the past algorithm constructed by a random graph, this random graph is called doubling graph. In the doubling graph, we have two axes. One axis is time and one axis is the state space. And from every possible state in every possible time, we start a Markov chain and we merge them when they meet in some point, like here. This Markov chain, constructing this Markov chain, this random graph, it doesn't depend on the Markov chain become positive or null. But in the positive recurrent case, it has some interesting property, and this interesting property is that if we look at this random graph in this case, it has one by infinite path. Some unique by infinite path that this green one, that if we look at the intersection of the random this by infinite path with the time 0, this point becomes a perfect sample of a stationary distribution of positive recurrent Markov chain. And actually, the coupling from the past algorithm give us this point. When we construct this algorithm, when we start this algorithm, if it is stopped, it gives us this point in positive recurrent case. In the non-recurrent case, also we don't have a stationary distribution. We don't have perfect sampling in classical sense, but we can look at the same doubling graph and consider the properties of this doubling graph in this case. In this case, we don't have the by infinite path anymore, but still we could look at the intersection of this graph with time 0. This intersection it's random set, as you see here, and using this random set and the graph, we can define some random measure on the graph. This random measure has some interesting property. That in this interesting property is that if we look at the expectation of this measure at each point of the state space, this expectation is equal to the stationary measure of the null-recurrent Markov chain at each point. It means that for a null-recurrent Markov chain, we could construct a random set. This random set has these properties that if we look at each point, the expectation of that, the value of that the measure in that point is equal to the stationary measure of null-recurrent Markov chain. Using this property of this random set, we define a perfect sampling of the of a null-recurrent Markov chain. And in the next steps, we try to construct this. We construct this random measure as a perfect sample. And in some cases, we have some answer that we can construct this measure. It's finished. Thank you.
So, any questions in the room or on the bridge? We have one question. There is in one of your drawing, you have some points. So I understand the horizontal axis each time, and then you have some horizontal, vertical dimension in which you have some points. Each point, is it a state, in fact, in the Markov chain, or what is it exactly?
It's the state. It's the state.
Okay. It was for me to be clear.
Yes, I just consider now a simple state that it's 0 to n, for example, but it's a state. Yeah.
Okay. And then what at the end you were presenting some I think it was a publication, or at the end one of the last time you have actually you have
yeah.
Yes.
Here is.
So this is some results that you obtained that
yes.
you will publish, or you?
Yes, yes. It is now. It is in archive. Yeah.
What? So I suppose that you succeeded to prove something new.
Yes.
Can you just explain shortly what is your contribution?
Okay. Actually, my work was to considering the properties of the graph itself, not to look at the perfect sampling and look what is the difference between this graph in null-recurrent case and positive recurrent case, using some properties of random graph to show that, for example, this intersection is infinite, but the measure this. Because it is not obvious that when we construct some measure on this set, it has the properties of the some measure, it is locally finite or something like that. We using the properties of this random graph and using this fact that it is null recurrent, we prove that this set, for example, is infinite and has defining this measure, it is locally finite. And it has this property, and it can be considered as perfect samples. And we define another dynamics and other measure. It is not the only measure that we define respect to null-recurrent Markov chain.
I remember a discussion we had last year. I think there is the things occurs when the number of states is infinite. In fact, no,
in the null-recurrent case, all the time the number of the state space is infinite.
Yeah. I remember the discussion.
Yeah.
It was not clear last year.
Yes.
Okay. Other questions? No. So thank you again. So next is Pierre.
Bien. Non, c'est juste qu'en fait. Hello everybody. So my name is Pierre Popineau, so I'm a PhD student and Professor François Bacheli. I'm going to present just shortly my PhD topic, so stochastic geometry and wireless network. So all this work has been done under the ERC NEMO, which is funded by the EU Horizon 2020 Innovation and Research Program and funded by the European Research Council. So just as a quick introduction, so what is the common point between the location of trees in the forest, infection loci in an epidemic, which is something that has bothered us for the past 2 years, actually, and users connecting in a wireless network? And so the simple answer to this is that all these three phenomena can be modeled using stochastic geometry. So stochastic geometry is a very powerful tool to model a lot of spatially correlated processes. And our main topic of research here is the use with wireless network. And so the motivation behind this, is that the next generation of wireless networks, so 5G, then the upcoming 5G advanced and maybe 6G in the forthcoming years, are becoming more and more complex. So we have to deal with layered and multi-tier network with mobile user and especially highly mobile users. We have to take into account cross interference, multiple frequency band, beam-based communication. And this leads us to wonder, for example, to how to design new association policies and new access rules to networks in order to maintain some network performance and even to optimize the network performance for all the users in the network. And so stochastic geometry has proven to be a very powerful and versatile tool to model such wireless network in order to propose a new network architecture to preserve these network performances. So I say that it is a versatile tool because it allows us to do two very different and yet very interesting analysis for wireless networks. So the first one is just the stationary analysis, where we are only considering an already established network. And this allows us to obtain network metrics to study, for example, the network performance for a typical user using a system level view to, for example, get the average or the expected Shannon rates that you can get from a phone, for example. And so this part of stochastic geometry has ties with palm calculus and random graphs, and is very, today it's a very hot topic when it comes to the study of wireless networks. And the other one is through dynamic analysis. And so this is a part of something a bit broader that is called spatial birth and death processes, which is a subclass of continuous time Markov chains. And with this analysis, we can study, for example, the stability region and stability criteria for such networks to obtain stationary distribution and maybe to obtain some properties of the stationary state of such a network. And so this part of stochastic geometry has ties with the queuing theory and ergodic theory. So these are two completely different sides of the analysis of a network that we can conduct with this simple tool that is stochastic geometry. And so when it comes to the work that I'm doing right now, so when it comes for the dynamics of wireless networks, so about the study of the stability region and the study of stationary region properties. So for example, we can prove that in wireless networks, you can get clustering. We can study the service times, the heavy traffic limits for the networks. We have a paper that is due to be submitted for review, which is joint work with François Bacheli and also in collaboration with Cephalotchner and Sergei Foss from the Hayat University in Edinburgh. And when it comes to the stationary, the stationary analysis with the design of association policies in 5G wireless networks. So we already submitted a paper in proceedings for GlobeCon 2021 about mobility-aware association policies for 5G networks. And there is another paper that is right now being written for WIOP 2022. And so this is a joint work with Sanket Sajay-Kalamkar, which was a former PhD postdoctoral fellow here at Link, now working with Qualcomm, and François Bacheli, my PhD advisor. And so this is my presentation. So if you have anything, if you have any questions about my work, feel free to ask. I'm here to answer the questions.
Thank you very much. Questions? So, will be the only one to ask a question today. Okay, I will ask one. Can you go back to the? Sorry, I didn't see you there. So.
Yeah.
Can you briefly describe the mobility-aware association policy?
Yes. So the thing is now. With the upcoming 5G protocols, we have to use something which is called beam-based communication, because before for the older protocols, the antennas was broadcasting the signal in all directions without discrimination. Now what we're trying to do is to make very narrow beams, which allows us to give to the mobile user a much more powerful signal. But the thing is, these beams, because they are very narrow, we have to take into account the mobility and especially the intra-cell mobility when you are moving around an antenna. And so the goal here is to take into account the mobility of users inside the association policies. And so the way we are doing it, so in the first paper, we designed a very simple association policy where we only took into account the mobility. So we completely reject it. So just to a bit of background, the classical association policy you have for a phone is the max power you receive. You always connect to the antenna that gives you the best power. When we designed these new association policies, we decided to remove completely this assumption and to say, we already connect to the closest antenna, and then we want to discriminate depending on the velocity of users. So we assume that we have several layers of the network with different performances. And how can we design an association policy taking into account only the velocity, removing the power consideration that depends only on the velocity? And so this was quite interesting because we managed to prove that in this particular class of association policies, there is one policy that maximizes the expected Shannon rate that you can get. And so this amounts to some optimization problems to try and prove that some function has a maximum. And this is a problem that has been solved in our paper.
Thank you for the question. Other questions?
Yes, here.
Which dynamics are you considering for the beams?
For the beam, so in the paper we made something which is called a sector approximation. So we decided that so the beams there are 2 to the power of n beams. So in the numerical application it was 8, so 2 to the power of 3. And then we assume that when you are moving around the antenna, so if you have 8 beams, each beam has a beam width that is 1/8 of a circle. And yes, so the base station is static. The beams are static also. There's no tracking. And when the user is moving, you have a beam boundary crossing. And when there's a beam boundary crossing, you have a small amount of time in which the network has to update the beam in which the mobile user is connected. And so this acts as a limiting factor, because if you're moving too fast, then you always have to reshuffle between the beams of the same antenna. And so this is how we managed to prove that there is actually a maximum. And in a previous paper that was published by Sanket, he proved that there's also an optimal number of beams per base station, considering the user moving at a fixed velocity, for example. So it's a multi-factor optimization problem.
Because between the static and the tracking, you can have something that is intermediate, where you have reconfigurations based on certain states.
Yes, definitely. So this is another field of research, and also, even if you're removing the tracking, but you can also have something, I think it's Guodong that is working on it, with reflective surfaces that you can add as a secondary signal source. So yes, right now it's a topic that is highly debated in the wireless networks community.
Thank you. So the last question? No? So thank you. So now, Maxime.
Can you hear me?
Yeah.
Okay.
So Pierre, can you stop?
Yes, I'm trying. Yes, sorry. Yeah.
And can you see the slide?
Not yet. Yes. No, yes.
Okay, great. So hello, I'm Maxime Raynal, and I'm a PhD student in the University of Grenoble and in Nokia Bell Labs. So in the links, my supervisors are Marc-Olivier Buab and Élie de Palafieux, and in the Université de Grenoble, it is Georges Queneau. So today I'm going to talk to you briefly about my PhD subject, which is towards automatic parsing. So I don't need to describe to people in the links how omnipresent and important telecommunication networks are. And I think I also don't need to describe in length that telecommunication networks, when you want to monitor them and troubleshoot them nowadays, it's problematic because they are huge, they are really heterogeneous, built with a diverse range of technologies, and they're critical, like really critical. We can't afford shutdowns every now and then. So we have to automatize monitoring. That's a necessity. We're currently doing that in many fields of research, but there's one obstacle which remains, which requires a lot of working, it's parsing. Because basically the way our networks provide us information is based a lot around logs and commands output. And all of these are actually unstructured text. The problem with unstructured text is we don't provide algorithm, especially analysis algorithm, unstructured data. It doesn't work well. We need to structure this data, and we do that through parsing. We parse the data, we type it, we put it in databases, and then we analyze it. And parsing is still done by hand. I mean, people write their own parsers by hand. So our goal, our solution is to design an automatic parser. In the little time I have today, I cannot go in the detail on every step which is required to build an automatic parser, but I will give you an overview of my work and what we've done so far. So the first part is about log clustering. basically, when we want to parse completely a log, we need to become aware of every template there is. So the first step is to discriminate and cluster the lines of this log according to their template. For this, we developed a new distance, which allows to compare string not at the character level, like it's usually done, but at the pattern level. In a way, generalizes the Levenstein distance or the Smith-Waterman distance. And we obtain really good result with this. Basically, we have the most accurate log clustering tool in the literature for now. It's not the fastest, but it's the most accurate. And it's been published in Algotel last year, and this year it's going to be published in the International Pattern Recognition Conference, along with reproducible science. We will open our code and let anybody play with our experiments. So this was the first half of my PhD in a way. The second half is dedicated to regular language inference, because when we want to parse, once we have identified all the lines belonging to a template, we need to infer this template. So for that, I have two approaches at the moment. One is using a meta-heuristic. Basically, the concept is to grow and maintain a population of abstract syntax trees, and the best candidate abstract syntax tree will be the language we try to infer. Another is using deep learning method. It's basically, I'm trying to use natural language processing method and apply them to regular language inference. Both of these are work in progress, and I hope that solving the same problem in two different ways can help us focus on explainability of deep learning results. Also, as a future work, which has started already, we have a prototype, an internal to Nokia prototype, which can parse automatically. So we are integrating building blocks one at a time. For now, the regular inference block, the inference block to infer templates is not fully operational, but it's going forward. And one of my hopes is that for the end of the PhD, there's a real completely automatic parser which can be released. So that's all. If you have any question, I'm here to answer.
Thank you very much. Any questions? Yeah.
Yes. So usually, when you build the abstract syntax tree, it's just the first step. And the second step is to do something with the tree. Do you have any plans?
In this case, it's the abstract syntax tree is the result we seek, because the goal is given a set of strings of word, we want to infer a regular language representing this word. And one way to represent a regular language is a regular expression, regexp. So basically, I'm generating abstract syntax trees, and the good abstract syntax tree is the regular expression which will recognize the examples. That's why I'm basically in this algorithm, the AST is the result. We don't use it, we build it.
Okay, but maybe the level of the abstract syntax tree is too low as it is at the character level of
I'm not sure I understood the question.
Well, you are building a regular expression for the entire file, not for elements that you may want to recover.
Just I'm looking for a template for a subset of lines which are homogeneous.
Oh, okay.
And I try to find the one abstract syntax tree which has, which on one hand will recognize, like will describe a regex which recognizes all my examples. And I'm also trying to have this AST as small as possible to have a readable regex, because the purpose is not to have unreadable results, and to have also something very accurate, very precise, which will not recognize too many things.
Okay, thank you. Other questions? No? So thanks again.
Thank you.
Next one is Bharath Choudhury.
Wait, accept that.
You have to select one. You have to select one. The first one.
You have to share the screen. Yes.
Oh. No problem.
What we see is not the display, is the viewer, the presenter.
Close it again. Okay.
Just
yes.
Why? If anyone in the room can help us, of course, is welcome. But no,
I could. You could use PDF. You have to start. First, start the presentation.
Yeah.
And then after you add tab, and then you go to Zoom and you select the presentation.
Yes. So maybe can do this.
Yeah,
then you share the present. What is the thing to start the presentation here?
Yeah.
Okay. And then you go to Zoom.
Add tab, and then you select the
Partager. Is it this one, right? Yes. Ecran number 2. Partager. Is it okay? Okay.
May I start? Good afternoon, everyone. My name is Choudhury, and I'm doing my PhD with François Battery and Bartek. Today, I'm going to talk about genealogy of records of random walk. I start with the first question that I start with the following question. What do you see? What do you see when you climb the tip of the Mount Everest? As you know, Mount Everest is the tallest point on Earth, and I cannot imagine myself climbing there, but I could imagine climbing on a random walk. So I would define, what do you mean by the climbing on a random walk? So I take a sequence of IIDs. I call them marks, and they're indexed by the integers. And I can visualize them on Z, putting these increments on the top of the edge between every index. And these increments take values from -1, 0, 1, 2, 3, and such that the expectation is 0. Now I define a map for each index on Z
and I map it to the next next index j greater than I, such that the sums starting from I to j minus 1 is greater than or equal to 0. It's the first j such that you get this. If you don't find such an index, then you map it to itself, I to I. Here I show one example. This is one realization, and the increments are -1 plus 1. And you see 1 is mapped to 3 because here 1 is mapped to 3 because, like, if you're starting from 1, you sum the increments, and first time you get this 0 at 3. Similarly, the same for 0. 0 is mapped to 6 because there is the first time the sums are reaching to 0. I call this a record map. You could not see here on the web, but I couldn't see in my laptop. I call this as a record map because of the diagram, the middle diagram. You can see that 0 is mapped to the 6 because it's the first time the random walk starting at 0, it reaches to the same level at 6. And 2 is mapped to 3 because it's the first time that the increment is greater than 0. So that's a simple rule. Now, I plot the same record maps in terms of the graphs. The last picture in the bottom, you see this. It's the same picture on the top, but plotted as the records. I just removed the trajectories. I just plotted them as records. You see 0 is mapped to its parents. I call this parent because it's a record of 0. And it has 2 children, -1 and -2. These are the -1, -2. You get the records at 0. I plot this graph. Now, what we do is that if you take a random walk with increments as satisfying the previous slide, so what you get is the object called eternal Galton-Watson tree with the offspring distribution xn plus 1. It's a very popular tree, and it is a universal object, and it's studied very well in the literature. And if you perform a record, it is the same as going to your father on this graph, on this graph. So if you perform the record on the trajectory iteratively, and what you get in the local limit is something called eternal Kesten tree, and it has an offspring distribution xn plus 1 hat. The hat means that it's a size bias distribution. And using this, you could see in the limit of applying these records, what do you see in the limit? This is a picture. In forward time, you just see the random walk. In the past, what you see is that you have a random variable z, and which is distributed as size bias distribution. And then from there, you choose uniformly a random variable k between 0 and z. And you run the random walk such that in the past that you stop at the first time it hits that level k. And then you iterate this procedure every time you hit this level. And then similarly here also you take a random variable z, and then you choose a k uniformly between 0 and z, and you let the random walk hit the first time it hits that level k. So this is what you see when you reach in the limit. So what do you see when you climb to the record of the random walk? You will see a decreasing sequence of mountains that you have already climbed till now. Thank you. I will stop with that.
Questions? I have one on my side. Can you give us some example of application of this to solve some problems in any domain? Just to see how this kind of study can be applied in some real world problems. Do you have some example?
Actually, record structures have been studied very well in physics. It's physics literature because so there is something called metastability in physics. They do the what happens is that system goes into stable. System doesn't reach the stationary limit in short duration. It takes a lot of time. So the records are seen like something like you are shifting from one metastable state to another metastable state. So they use that to study the statistics of it. But they just do the scaling limits of that structure of the records. So what I did is here is a local limits, like in the sense like if you move to the records, next record, and what do you see like the different records you have moved already? Like what is the distribution of them? You could compute like what is the gap between the two records, and how that's what I call the genealogy of records. Because you see the first record here, the topmost record, and the next record is here. And you could compute many functionals, like the gap between the two records, and then how much time does it take to get a next record. So all these things.
Okay, thanks. Other question? Yeah.
This one? Oh, sorry, next. Okay.
Do you understand why
2 is mapped to 3 because you see from the middle picture, you can see that it's the first time the sum is just increment is greater than 0. And 3 is mapped to 5 because first it goes to the -1 and then +1. So the sum is equal to 0. So I defined the map previously as the first increment, first time that from I you sum the increments, and first time you raise greater than or equal to 0, and you map to it. So that's how.
Just a comment for me, the formula was not clear, but when I saw the
picture,
the graph, it was.
Yes, so that you hit the same level or above the your level.
Better the rules on the drawing than on the formula.
Yes, so it's easier.
No, just
so,
to comment.
Thank you.
Other questions? So thanks again.
Thank you.
So I think it is the last talk, if I'm right. Guodong, yeah.
We open it first.
Yeah, first.
How about the way?
You need first two.
Yep. And here it's where I got lost.
Okay. Hello, everyone. I'm a CIF PhD student, joint supervised by Nokia and in Inria. My academic supervisor is François actually, and Nokia advisor is Stefano Paris and Luis Garcia. My work is about what is the best candidate for next generation wireless network to assist net wireless network. As Pierre said, he started on MIMO, and which MIMO is to focus a very small beam to focus the energy to a particular direction. And some people suggest we can use more and more active antennas to form more and more even stronger energy to the user. Then the problem arises is it can cause some health concern. Despite this radio wave does not transmit COVID virus, but it indeed causes very high electromagnetic field, and then it might hurt people's skin and everything, and it even waste a lot of energy if we implement all the active antennas. So what to do is we want to implement some passive or semi-passive antennas, which can reflect the signals by absorb some of the energy in the environment and direct it to the user. So in my work, I started the comparison of how to configure this big antenna surface named reconfigurable intelligent surface. There are two schemes named beamforming, means all the small antennas work cooperatively to beamform some energies to the user. Another scheme is scattering, means this big surface works as a pseudo-random scatter. Then it could create a rich scattering environment and create a high rank channel for the MIMO, because because it then can improve the multiplexing performance for MIMO. The first step is to study to compare these two schemes. Is beamforming better or scattering? We find that in some case, for example, if there are very good line of sight condition, we use beamforming. But if there is some obstacles and that create scattering environment, then if we apply we configure the race as scatter, then we can increase the energy level of scattered signal. The final objective is we apply stochastic geometry to study this system at a system level to see if there is in a very big area, there are plenty of base station, plenty of user, and a lot of race. Then what is the performance gain by configuring beamforming or scattering? Of course, comparison between beamforming and scattering is the objective of research, but the objective for the final objective is to check is this entity, the race, is meaningful for next generation communication system, because it costs a lot of money, but if the gain is trivial, so why spend this money? And yes, so that's it.
Any questions? No?
Yeah, one question. So I don't know these topics, etc. So in the stochastic geometry modeling framework, have been already some models proposed for scattering and beamforming, I guess yes and no. And are you simply reusing them, or do you have to propose something new also from the point of view of modeling? Right? Methodologically, what is the challenge you are trying to solve?
Speaking of the beamforming, yes, because Pierre has done this. For beamforming, there are some very mature tools, frameworks to model this, but for the scattering, it is missing. So the past 6 months, I'm focusing on the scattering part.
And how do you validate your model of scattering, for instance, via simulation?
Yeah, simulation, root simulation, compare with the stochastic, the closed form equation obtained by the stochastic geometry.
Other questions? Yeah.
Thank you very much. My question is not about your talk. It's just to know if you have information about what is the state of the art in RIS, in reconfigurable intelligent surfaces. What is feasible today?
You mean the implementation, or?
Yes.
Yeah, the implementation is now it's like ideally people want each element of the RIS can the phase of each element can be changed from -pi to pi, absolutely continuous. But the practical state of art is we can design 2-bit or 3-bit phase shifter for each attendant element. So it's kind of discrete beamforming or discrete scattering, I think.
Other questions? So thanks again. All the speakers, everyone was in time also, and it was very interesting to see all what you are doing. Thank you again to all.